So, hello, and this will cover the introductory practical exercise on our telecom course. Yes, so basically we are going to use Matlab. Right now I'm opening it in the browser. Yes, but you can also use the standalone program or Octave as well. That's an alternative. Yes, Octave. However, I have some issues with it in this laptop, so I can't use it. While it's loading, let's maybe go through what are we going to do today. So today, what we want to do is to have some example of adding noise to the rectangular shaped signal, and we'll try two types of rectangular shaped signal with different voltage levels. Yes, so basically the first task will be just to generate some data, ones and zeros. Either you specify them directly or you can generate them randomly. I will show you both options. Then what we generate here is going to be a discrete signal. Yes, we, however, as we discussed, want to have something like continuous signal or as close as possible to it in a computer. Yes, so we'll do the conversion of that to unipolar pulses, hello, with amplitude of 1. And also I will show you how we can display these signals in Matlab. So some basic stuff like, generate some variable, add something to that, convert discrete signal into the continuous one, how to display the plot of it, and all that stuff. Then we are going to add some Gaussian noise with a signal to noise ratio 20 decibel and display the signal with noise. Yes, so it should look, so original discrete signal looks like this. Yes, we have only samples 1 0 1 0 1 0. Then we convert it into the continuous one, which is now rectangular shaped pulses like so. Then we add some noise to it, so it will look like this. And the next step, what we are going to try to do is to clean the signal out of this noise by comparing. In this particular situation, we are going to compare with a threshold of 0.5. If our point is above, it's 1. If it's below, then it's 0. Yes, so as you can see, in that case, we can get a very smooth and clean signal. However, this is only thanks to the relatively high signal to noise ratio. Yes, we have good conditions here. We'll also try to change signal to noise ratio and see some issues which may arise from that. Yes, you also have some code fragments here as well. Yes, which you can copy and paste basically, but we'll go through that in now. Yes, uh, so okay, let's try a new session then. Well, actually, I believe Octave should work. It's just I don't have editor working, which I still can get around by creating a file in Notepad++ and working there. So let's try this way then. And in case you already have the Matlab access, then you can, as I said, access it through this web page. But for some reason, right now it's not working for me as well because, well, this is a cloud platform and also this computer is a little bit old. Although I don't think it should be an issue. It's actually good that it's a cloud one, yes, but anyway, this is the button Open Matlab Online. We'll try it now, and also I am going to create a new file, new script. Let's check if it works. So let's say this is going to be telecom practical exercise 0. And let me try to run it. Yeah, so this one is not going to work, but if I were to run it from here, it also doesn't run. So let me then see what happens in it. So just a minute. Why? So it's some issue with my editor that has changed encoding, yes, which I don't really want to, you know, tangle around now. So instead, no. So instead, I want to open it in external editor, some Matlab files, so telecom practical exercise 0, and see what's in there. Oh yeah, so as you can see, it's some funny stuff there, which I'm going to delete. Clear variables. And if I try to run it now, okay, so seems I need to make a new one. No. And I delete this one. I make a new one. Some technical issues on my side, which I'm sorry about. I was hoping the Matlab Online would work, but it doesn't. Telecom practical exercise 0 mat file. So oh yes, now it's working. Yes, so I will have to switch between Octave and, but normally it's not an issue. Normally everything should work fine. I just, should reinstall probably this Octave and it should fix the issue. Yes, Matlab Online is still not working sadly, but these computers should have it installed. Also, if you are trying to work on your own computer, we can actually even use Octave Online. Yes, so that is also an option. That's it's just you need to, I suppose, log in with some kind of a Google account or something, yes, to be able to create a file. Yes, so let me just demonstrate this also as an option. It doesn't produce so smooth pictures though, but it's going to work. Yes, so also I prefer not to use online platform before. It seems like internet here is a little bit slow for Wi-Fi at least. And well, yes, you can sign in with Google account, then you will have option to create some files here. Well, let me actually demonstrate that for you as well. Today is more important like to get you on how to run Matlab, how to run Octave, whichever you can access, yes. As for the code, it's going to be exactly the same for both of these, yes, so they are perfectly compatible. Hello. So basically, whichever is more convenient or more accessible to you, you can use that one. And well, basically be it. Yes, so again, some Wi-Fi issues. Well, also, okay, while it's thinking and letting it to login, let us maybe begin. Yes, so as for the first step, we can choose a random sequence by simply creating it. Yes, so I can say that this is now you can create comments in Matlab with a person sign. Yes, basically. Now in Octave, the hashtag and person sign will work both, yes, but real actual Matlab accepts only a person as a comment. Yes, so basically this is task one, get some random data. We'll call this signal as S a small letter. Yes, so basically and specify some sequence separating the numbers with a comma or semicolon. Yes, there is a difference actually, which I will demonstrate. Yes, it's simpler just to demonstrate. So I basically, think of some data. You can think any other sequence. I just use ones and zeros and nothing else. So I save this now. I then try to run it. And as you can see, it has now created a variable of the class double with dimensions of 1 by 9, containing 9 ones and zeros, yes? Now, if I were to separate these numbers with the semicolons instead, let me make another one, S1, semicolon, it's going to create another dimensions. So save, run. As you can see, now we have S as a vector row and S1 as a vector column. Yes, so basically MATLAB is actually taking its name from the fact that it's oriented to working with matrices. Yes, and you can even specify the matrix as follows. Yes, like this, for example, 1, 2, new row, 3, 4, 5, 6, and so on. So you separate the columns with the comma and you separate the rows with a semicolon. And you can actually have multi-dimensional arrays as well. Yes, like 3 dimensions, 4 dimensions, 5, and as many as you'd like to. But we are not going to do that right now. Yes, it's just like a simple demonstration. So it actually matters whether you use colon or comma or semicolon. Also, as you can see, once I have created this signal, now it produces any output of any operations that I have. So I have, let's say, signal S1 10 symbol, signal S of 9 symbols. So let me actually make them equal length. Now let's say I want to have S plus S1 to be calculated as a summation of some sort. Let's see if it actually handles this. Oh, sorry, the wrong line. Well, it did, but in a funny way, which we did not expect, yes? What it did, it took this entire row, this entire column, and created a matrix of 9 by 9 by actually having everything added here. Like you take this row, you take this column, add everything together, and accordingly, yes, you see that it's produced this column. Then you take uh, it again, yes, and you produce it again. So basically, it's like you take this one and add to this entire column. You take this one, add to this entire column. Yes. Now, if we were wanting to get them well properly, like 1 plus 1 is 2, 1 plus 1 is well basically our only first column, and that would be just one column, you would have to transpose this one to become as a row also. In MATLAB, there is a very simple operator for that, which you can use is an asterisk, like so. So now I have specified it as a column, but I also said I need to transpose it. So for that reason, yes, it's now also as a row, and it added 2 rows properly. Yes, so you need to pay attention here. What are your dimensions and whether you try to do everything correctly, because, well, it works for adding, like so, yes? Now, however, if I try to multiply these 2 arrays, it's going to be different depending on what exactly are dimensions. So right now I have a first as a vector row, the second as a vector column. So ideally it should have one number, which is going to be sum of all of the squares. So it takes this one, this with this, all of them one by one, and adds together into one number. Yes, so let's see if it is the case, which indeed it is, yes, although well, yes, it's actually multiplying like so. Now, if you transpose S1 and try to multiply row with row, like in mathematics, yes, it's going to say that's impossible. Yes, you cannot multiply vector row with vector row. So that those dimensions are very important in math. Yes. Okay, so I'm going to keep this as a vector row. Also, let's check if the octave actually connected. Okay, now it's connected, yes, and I have logged in with my Google account. So now, as you can see, here there is this file list where you can either create a new file, like for example, my script, yes, and then you can type all of that stuff I have here. Dismiss, all dismissed. Which is going to be saved in the cloud, yes, and there is a button run, like so. Although, as you can see, it has some, timer here, which makes it a little bit inconvenient, especially, well, I didn't save, yes, so it now actually worked hello world and nothing else. So you need to make sure that once you have want to run it, before that you need to press this to save, yes, because I don't have any more here hello world, as you can see, but it still produced it based on the cached version, yes, so you need to update one. Okay, so now as you can see, it produces these numbers. You can also construct the plot, as we are going to do next, with the stem command of signal s, which is going to produce the picture version of this signal as well. Again, I didn't save it, so I have to save first. Yeah, so now you can see that it actually displayed a plot of this inline of this command line. So you can actually use this one easily as well. But since I already have this issue solved on a sort of, and plots are a little bit better in the desktop version, so I'm going to stick to that one, yes? So let's now display this discrete signal. So there are multiple functions for trying to display pictures. You can use, for example, plot of signal s. Normally, you need to specify two parameters, what you have to display on x-axis and what you want to display on y-axis. If you specify only one of them, it's going to assume you specified y-axis, and it's going to automatically use 0, 1, 2, 3, and so on the x-axis for you, yes? So basically, having this, sorry, having this is producing this plot, yes, consisting of multiple points connected with the line. So if I want to, I can actually say, please also display the points themselves. So I can specify the style. Let's say I want to use asterisks and some dashed line as a style. And furthermore, of the red color, yes? So basically, this is the marker, this is the line style, dashed, and this is the color, red. Yes, so if I run this now, you will see each point, yes, 1, 2, 3, 4, etc., connected with the line. That is how plot function works, and we will use that to display continuous signal. Discrete signal, however, as we discussed in the lecture, exists only in the certain moments, sampling moments, and outside of these moments, there is no signal in between, yes? So the plot, hello, is not actually the most suitable function for us. Let us try another one called stem. So stem is going to produce these small branches, tree branches or some sort of, yes, which will look much more like discrete signal actually. Yeah, so now you can see that it actually is 1 1 1 0 0 1 0 1 0. Yes, now pay attention that it starts numbering from 1. Yes, here there is no signal at 0. Well, that's an issue of Matlab. It actually starts from 1 to and goes all the way up to the length. So basically 1 2 3. I didn't specify x-axis here. Because of that, it automatically puts these numbers. Actually, it's exactly the same as if I were, no, I don't want to reload it. I actually want to close it. If I were to specify here, just saying, okay, x-axis is going to have plain number starting with 1 and going to 9, which is the number of points. Well, actually, we can go even smarter about it and say, please, let's calculate how many of the points are there. And here you can see that I have added a semicolon at the end of the file. Now, in C programming language, for example, if you don't add semicolons, it's not going to work. In Matlab, it's optional. So let's see what it actually does. No, I don't want. Uh, and just a moment. Okay. So it's reading it properly. It's about the stem command. Okay. Something is wrong here. I have changed it. One to nine. I suppose it might be of this formatting. Let's remove it for now, make it as simple as possible. Okay. Okay, so that probably was it. And now, as you can see, because after the line here, n is equal to length of s, it actually didn't say what is the n. Yes, it did it silently. Yes, as you can see, it said s is this one. N is not here. So if I remove this semicolon now and save the script and rerun it again, it's actually going to produce the output as well. Now, for some reason, stem is getting some mistakes here. Or maybe because I didn't close the picture of, yes. So it seems I have to close it when I rerun the program, yes. We can actually automate that and say here also, in addition to clearing, let's close all, yes. Let's close all pictures, yes. Because for me, it's producing some issues, although it shouldn't. But as I said, my Octave version is a little bit unstable here. So now, as you can see, it displays n is equal to 9. So this way, you can actually suppress any unnecessary output, yes? Like if, let's say, I don't want to know this and I don't want to know this, then it's going to do command silently and display no output whatsoever. So you can choose whether you want to print the result into the command line or not. So let me keep these because these are quite short and not really a problem. This way, actually, when you specify it now here as an n, yes, you can change the sequence as you like, and it's going to adapt automatically to that. I added some more numbers. There is no more 9 of them, like 12, yes, but the program actually read it itself that now it's 12 of them, and actually we can, update plot. Now, what if I want this to be going from 0, not from 1? Well, for me, since I now specified x parameter, it's easy. I just subtract 1 from here and 1 from here. Now it's going to go from 0 to n minus 1 and display these samples. I suppose we can still use red color. If you'd like to see the grid lines, so you can also specify grid on. Now pay attention that stem does not produce any numerical answer. Yes, it displays a figure window, and that's it. So it doesn't matter if you use semicolon here or you do not. Yes, it doesn't produce any output in the console. So it's neither anyway. Although sometimes, as you have seen, there was some error, some callback, which I suppose if you put the semicolon might be, disappearing. So actually, it's a good idea not to put the semicolon here, because if something goes wrong, if there is some warning or whatsoever, you may not see these because of you suppress the output. So again, I'm going to save it now, run it again. Now you can see these grid lines also. Now I want to also add X label and Y label to this picture. Well, it's very simple actually. Yes, you say X label and in quotes, either a single one or double one, it doesn't matter for Matlab, specify the text you want to see under X label. So this is going to be number of sample. And Y label is going to be the signal value. Or we can simply say, let's say for simplicity, data that we want to transmit. Yes, ones and zeros. So we save it. Now it actually produces the labeled ones. You can also add title, legend, and many stuff, which we will gradually during the course learn more and more about. But as of right now, well, we'll stick to this one, yes? Also, what if I want each time to generate some new random sequence, yes? For that, you can use the function called random integer, rand-e, yes? About any function, literally, you can find in this course or wherever else, you can get built-in help by specifying help rand-e, for example, like so. And it's going to say you how are you supposed to call that function and give some examples as well. So as you can see, rand-e only needs to know if you want to generate one number, maximum, what is your maximum? And then it's going to generate random integer that is without floating point in the range from 1 to maximum, yes? However, we want to generate numbers from 0 to 1, not from 1 to maximum. So we'll be, a little bit cheating about it. Yes, like say, okay, we generate numbers from 1 to 2 and then decrease them by 1. Now, if you want to generate a batch of them, or specifically say I want minimum to be 0, like so, you can do that also. So let's try some examples. So run e of just maximum 5, for example, is going to produce a random number every time you run it in the range from 1 to 5. Now, if you want to have multiple numbers, like let's say 10 numbers, it's going to produce a 10 by 10 matrix. So you have specifically to say whether you want 10 rows or you want 10 columns or you want 10 by 10 both. Yes? So this way you can actually generate the data in this way. Now let's say I want to generate data from -5 to +5. So instead of simply specifying maximum, I specify an array here with minimum and maximum. So now it's going to generate random numbers from -5 to +5, yes, including 0 as well. So there are two ways accordingly how we can deal with this problem, yes. Now let's say I don't want to remove this, I want to comment it, yes, like so, and say instead let's calculate s as a random integer of some number, yes, so starting from 0 and going to 1, and we want to generate some number of them. Well, ideally, actually, we would say like n, but in this situation, it doesn't know what is n because s still doesn't exist. So you first have to create s and then read one. So for that reason, I'm going to go around here like this, hard-code parameter 10 here, which is, well, maybe not a good idea, yes, but you can also do it like this, m, and say m is going to be 10. So this is number of randomly generated bits. Yes, so let's say each one of them is bit, 1 or 0, and accordingly, well, we generate them randomly. Now, why would we need n in that condition? Well, it's a little bit rudimentary here because m is going to be equal to m if you have this line uncommented. However, if you were to comment this line and uncomment this line, it still is going to read how many other actually, yes, ignoring this m equal to 10. So m is necessary only if we generate them randomly here, and in that case, we might not even need this n at all, yes. But I just leave it for compatibility if you will want to switch between random sequence and your specific sequence. So you may want to generate sequence like this, for example, just to test it, yes, all of them ones or all of them zeros. Yes, so sometimes we may want to. Now, let's make this one random and see if it works correctly. Yes, so I have uncommented this line. And I don't worry about cleaning all of this console, neither I do work about this workspace where it has these variables, yes, because in my code at the beginning I added this CLC which clears console and clear variables which erases these numbers, yes. So if I run the code, yes, you will see that actually it first erased everything from here, then it created new variables. Now my random sequence actually includes only 2 ones. I don't like it, so I'm going to repeat the code, and it generated another sequence of ones and zeros. Yes, so every time you run the program now, it's going to produce a new random result. And well, this might be good for us and sometimes inconvenient. Because of that, there is actually a way to somehow freeze this random generator, to say that it still generates them randomly in nature, but every time you run it, it's going to be the same random sequence. Yes. So for that, you need to specify a parameter called seed. Yes. So let's see how we can do that. Mm, so it's not, I believe it's not in here exactly. It's in the rand help or seed, I believe. No, help rand. Yes. So here you can run this command, run seed and some value. Let's say for the example, I don't know, 10, for example. Yes. So this way we are going to actually fix our random generator on specific random sequence. So it's still random, although every time you run the code, it's going to be reproducible random. Yes. So there is a way to achieve that. So you can see now it's 0, 1 here, 3 ones in the end. I run it again, and it is exactly the same sequence. No matter how many times I run it, it's the same all the way. Yes. So there is a way to actually force random to repeat over and over again. Or you can comment this line, and then random is actually going to produce really random result every time. Yes, like this, or like this, etc. So whichever you prefer, you can keep that one. We'll go further. Our next step is now to convert these discrete signal samples into the continuous line signal, which we can then send to channel, and where the noise will be added to that. So that is the task 2. Convert discrete signal into unipolar pulses with amplitude of 1, well, relative 1 volt, because in a computer it's not really volts. Yes, the computer doesn't care what is the unit here. It's just for our imagination that this is 1 volt, and display this picture as well. So uh, let's make the task 2. Task 2, convert discrete signal to continuous. Now, this is not going to be analog signal because it still is limited by amplitude. It can be either 0 or 1, nothing else. Yes. So it's actually going to be quantized signal, quantized signal. Yes. So that's a little bit different than analog signal. It's more specific one. Yes. How are we supposed to do that? Well, basically, all what we need to do is now say, let's zoom this a little bit, that I want this symbol 1 to repeat over as long until I get new point here, 0. So up to this point 0, ideally, in theory, I want to have infinite amount of these repetitions. So this 1, 1, 1, 1, 1, 1, 1, here we happen to have 0, then it repeats as 0, 0, 0, 0, 0 until this point. This point then repeats again, and so on and so on. Yes. However, in a computer, we don't really need infinity. Yes, we can think of, I don't know, maybe 100 points would be enough to actually cover this as a smooth, uninterrupted line. Yes, or maybe even less. Yes, especially if we'll start using a function plot that is going to connect these points for us. But, well, first we need to somehow replicate the symbol multiple times. So let's say we want to repeat this 0 100 times, we want to repeat this 1 100 times, and so on and so on. For that situation, we have something called a Kronecker product. Yes, so it should be displayed somewhere here. Here, yes, a Kronecker multiplication, Kronecker product. Well, it's a mathematical operation. You can even actually, Wikipedia it, Kronecker product. It may look a little bit intimidating, yes, looking at all of these formulas, but the idea is actually quite simple, and let me demonstrate you that with some example. So let me clear everything. Let's have a matrix A consisting of 1 and 2, and some matrix B consisting of 10 and I don't know, well, just 10. Yes, just one element in our matrix. So it's still scalar, but we can think of it as a matrix with dimensions of 1 by 1. So what I want to do now is to have, well, actually it's not actually a good example. Let's have matrix B as 1 by 2, like a column. So A is a row, B as a column. Yes. So what I want to do now is to have this 1 replaced by this entire column multiplied by it. So if I run Kronecker product, cron between A and B, I would get this first column as this B column multiplied by A1. Yes, so 1 multiplied by the entire column and replacing the symbol 1. Then I'm going to get the 2 replaced by this entire column multiplied by 2. Yes, so 2 by 1 and 2 by 4. So we replace of the original matrix 1, this entire matrix, yes, whatever it is, and multiply. So basically, if B were actually some matrix like this, 1, 2, 3, 4. You may notice that sometimes I use comma, sometimes I use just space. It's the same, yes, space and comma is equal. So you can use both of them and it's valid. It's what's different is a semicolon that says the row is finished and new row starts. Yes, so now I run Kronecker product between A and B, and now it takes this entire matrix, 1, 2, 3, 4, replaces this symbol 1 here, yes, and accordingly then it takes this symbol 2, multiplies this matrix, like 1 is giving 2, 3 is going 6, 2 is going 4, 4 is giving 8, yes, like so. And it can work with larger matrices as well. So if our matrix A, for example, was, let's make some simple example of diagonal matrix like so. Yes, so what we should expect now is that this symbol 1 will be replaced by this entire matrix. This symbol 1 will also be replaced by this entire matrix, and zeros will be replaced by 4 zeros. Yes, so let's see how it looks like from A and B. Yes, here you can see our matrix B. Here is our matrix B, and here you can see matrix B multiplied by element which it was replacing, 0. Yes, so entire matrix was multiplied by 0. Now this gives us a good way to replicate some numbers. So let's say I have A now as sequence 1 to 5. Yes, like so. What if now, let's say I want to repeat any number 4 times. So I want to have not 1, 2, 3, 4, 5, but 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5. Yes, how do I do that? I use Kronecker product for that with matrix A, and say I want to replicate it with this row, 4 ones. Yes, now the goal is achieved. Yes, now if I say with a column, it's going to actually do column wise now, like so. So you have to be aware of that. Since our original data was a row, we are going to replicate it with the 100 ones in one row. But typing it 100 times is a little bit tedious, yes? So we don't really want to do that 100 times. Because of that, we can use a built-in function called ones, where you specify number of rows and number of columns, like so. Yes, so it produces 100 ones as a matrix. So this way we use this Kronecker product, as it's said here. So SC in this case is our how it says. I don't honestly remember how we call this SC, But this is basically our resampling sequence, yes, which we are going to replace each symbol with. So C is 1. So no, I don't want insert. Yes, of course. Sorry, which comment? Whether you write here or in command window, well, actually, it's going to work the same. It's just the fact that if you write in the file, this file is going to be saved and you can run it. Yes. Now, normally, I would use this editor to do so, but my editor is bugged a little bit and it changes encoding and it doesn't work because of that. Yes. But if it were working, there is this play button which you simply press and everything works. Yes. So, well, actually, maybe, just maybe, let me try to look into this, take 1 or 2 minutes, and this will be fixed. Yes, so editor, we have some issues with encoding here. I suppose it's here, probably. Let's try this one. So ask, it was Unicode, and the Octo itself does not accept Unicode files. Yes, so I will close this editor now. I still have this Notepad++ open, so I will be able to resave it if needed. Um, but just in case, let me make a new one and say test. So this is the test file, which I'm going to, which I can't run, it seems, from the looks of it. Yes, so test file. No, it's actually working. Yes, it's actually working. I did fix this issue, but for some reason, this button doesn't work for me now. But okay, let me try now this file. Um, wait, telecom PE0, yes. Now it's open. Yet, let me zoom this a little bit. Save file and run. I haven't completed it. Well, actually now it works. Yes, actually it now works. It was really not so difficult to fix, although it changed some font here for this. That's funny. So let me comment this one. Yes, so basically here you have button to run it, save and run. Yes, and basically now it runs. Yes, as you can see. So that's how it normally should work. You shouldn't really need another external, uh, you know, editor to work with this. It has built-in editor and it works. So fine, we have fixed this problem. So only funny thing that is left is this one, but I suppose it's okay. So in command line, you can, just play around and test some things, like to get some help, for example. Help, I don't know, AVGN, the function we are going to use for the noise channel. So as you can see, it says you have to first load the package. Yes. Then you, say, okay, I'm going to load this package now, but I don't load it yet because we will need it later. And then you will get the help. Yes. And then you switch back to your code and write it here, for example, like it will do something to your code. Then you save it for later, go home, next day you open this file, run it, and it still works. And you don't have to run everything up to that point. Yes, that is the good idea of the script. Because if you were just to run this function, yes, let me just demonstrate it clear. Yes, let's say I want to have this stem constructed now. It's going to say, what is N? What is S? I don't know. Yes, because you haven't have them here. you have to first run everything up to this point. And that's where scripts actually come in handy, because this is a program which runs one by line, line by line, yes? So this way actually it works. Well, it's not going to work because of this. So this is going to be once, 1 by 100. Now, there is no point to actually display this one, yes, because, well, it's going to spam the console for me here. So I'm going to suppress this output by adding semicolon, and then I can create a signal called transmitted signal, STX, by using the Kronecker product between my discrete samples S and this sequence of ones. Now, STX is going to be cron between S and SC. Now again, I will want to put a semicolon here just because, well, it's easier to show what's happening in the console. If I don't, yes, we don't really want to see all of that. It's not much information for us. And also, actually, when it has to print this, it's going to work much slower. It computes this much faster than it displays. So actually, your program might run much slower than it can, only because it's taking some time for it to print it. So I'm going to suppress the output also. So here we convert discrete to quantized, yes? Thank you. Now we can display that as well. However, let's see if what happens when we try to do it blindly, like so. Yes, plot STX like this. Well, now we only see this first signal or second signal, and our first signal is gone. Yes, we don't see them both as we wanted to. We can work around this in different ways. First of all, we can say, okay, please create a new figure for this. That's a new window, separate window, where it will be displayed. So this way, it has a first picture in the figure 1, second in the figure 2. However, in this exercise, you may notice that I have somehow made them look the same together in one picture. That is also an option. Yes, you can say, instead of a figure here, hold on. That is going to freeze the existing picture, and any new picture you display is going to be displayed on top of that. Afterwards, accordingly, you say hold off. But it's going to produce its own problems. Yes? Let's see what exactly. Well, now you can see that because we have increased the sampling rate, yes, now our original signal was consisting of 10 samples only, and each of these 10 samples was repeated 100 times. So we have 1000 samples for the second signal and 10 for the first. And the scale, this looks like just the beginning. And somehow we want to, make them look in the same scale. Like this is the problem, yes, that STX is 1 by 1000 and S is 1 by 10. So 10 is only the first 10 samples are visible here. It's here, yes. Zoom like so. Well, it really goes all the way up to 10, yes, 0, 1, 2, 9, minus 1, and starting from the next point, well, 1,000 other ones. So how are we supposed to compress them? Well, we need to realize one thing is that here, well, actually, let me start the Epic Pen so I can draw on the screen also. What we want to have is that this one symbol or bit or rectangular pulse representing this symbol should also be over its duration of 1, if you will, 1 second, not 100 seconds. Yes, and same goes for here. So somehow we need to say that it's not 100 seconds for each pulse, but only one. So for that, we need to specify our X data. No, I don't want this. And you can do so by giving here some numbers. So our original situation looks like this. We have from 1 to, well, basically here you can say that this is some kind of n length of, well, actually, what's preventing us to finding the length of the entire signal, yes? So let's say L is going to be length of SEX. So that is number of quantized signal samples. So in a sense, you can think of it as analog signal, yes, equivalent in our computer memory. And accordingly, this goes all the way up to L minus 1. Sorry, I forgot. I just need to press this button. Now you can see that this is really 100 here, 100 here, 100 here. So when you specify this as a range, you can always, let me just demonstrate, yes, you can always say from 1 to 10, for example, as a range of numbers. But also, there is a way to specify the step. So let's say now I will specify a step of 3. So that means it's going to take 1, 4, 7, and 10. I can also specify the step of 0.1 all the way up to 2. So that's now going to be with this step, yes? So that means what we need to do now here is to go from the 0 to n minus 1. That is going to be this. And fill everything in between with some extra points so that total number of these points is going to be 1000. That step is 0.01, I suppose, yes, so 0.01 all the way up to n minus 1. Well, not exactly, because it produced actually one sample more than necessary. And it goes all the way from 0. Yes, again, a lot of spam, but here I actually wanted to see this, to see how it goes. Yes, so now I have, well, actually, well, wait a minute. Actually, no, actually, I wanted it to finish at 10. Yes, not 9 point, not really 10, but 9.99. Yes, so I have one symbol missing. So it's not like L minus 1, n minus 1, but it's more like n minus 0.01, like so. So now I have 1000 samples, yes, which includes the last point here, and I can specify it here. So let me create a new vector called time from 0 with a sample step of 0.01, because I have 100 points here, and this is inverse of 100, yes, so 1 versus 100. And all the way up to how many symbols do we have minus one step. So now if you specify this time here, for the second plot, because for the first plot we don't need to change anything, it's already as it should be. Now the second plot is now going to align with our first plot, yes? So I only don't like this orange color, so let me change it to, let's say, black color with the letter K. Also, I can use line width, which types like so. Just you need to quote it. Well, actually, I can try to do it this way. Well, yes, actually it works like so. Okay, I will use double quotes instead. Like so. Here as well. And here as well. So this is going to create this line thicker with a thickness of 2 in a black color so that it will be easier to see. Yes. Now we can a little bit move it like so. And so accordingly, you can see original sample and the, in a sense, analog signal representing this sample. So basically, in our case, we see that this sample continues to support this voltage of 1 volt until the next sample. So once next sample received, its level is maintained until the next sample. So that is the quantized signal. Yes, not really analog maybe, but it's as close as we can get. So what we want to do to that signal now is to add noise. Yes, that is the task 3. So additive white Gaussian noise. So we discussed last lecture why it is called white, because it's not depending on any previous values. It's having the infinite and equal spectral density and 0, and it's Gaussian because it's a normally distributed process. So there are 2 ways how we can work with this. Either we use a built-in function called AVGN, which is not working, calculating exactly as we want to, but it's convenient, or we can calculate the noise ourselves. So at this step, we are not really interested in being very accurate, so we will use the function called AVGN. Now, if you use Matlab, it shouldn't be a problem, and you don't need to load anything. It should work right away. In Octave, however, you need to load specific module if you have it installed. Yes, so I'm going to load it. You need to do that only once per your open Octave session. So you open Octave, then you run it, and until you close the Octave, it's going to be loaded. Yes. Now I have help AVGN, which says as simply as that. What you need to do is to say, okay, you are going to get a signal Y with noise after you specify your original signal X without noise and desired SNR. Yes, as simple as that. So basically you say, please add SNR, noise of SNR 20 decibel to my signal and give me the result. Well, as I said, we will learn how to actually calculate it more precisely than this function. And it is related to this power value, yes, which we don't specify here. But at this point, as I said, we don't really care much about whether it's actually realistic, too realistic or not. We only care about concept, that we'll see that our signal is now noisy, and we will want to try to do something about it. Yes, so task 3, add AVGN additive white Gaussian noise with built-in function. So as I said, as if we use STX for the transmitted signal, then we are going to use notation SRX for the received signal. And function AVGN adding the signal to noise ratio of 20 decibel to your original STX signal. So I'm going to use SNR variable here and define it at the top of my code, SNR 20. So signal noise ratio in decibel, meaning that actually signal is stronger than noise 100 times. Yes. So how was I able to tell it so fast? Actually, this number 2 says how many zeros you have after in your decimal points. Yes. So basically you have 2 zeros. That means it's 100. So 30 decibel would be 1000, 40 decibel would be 10,000, 60 decibel would be 1 million, minus 10 decibel would be 0.1, and so on. 0 decibel is 1. That means signal and noise are equally strong. So that's again very easy and fast way to convert these, full tens of decibels, like 10, 20, 30, and so on. So basically the first number says how many zeros. Well, now we want to plot this. However, we want to plot this not on top of what we already have. We now specifically want to create a new figure. And here we want to have a plot. X-axis shows time, y-axis show as Rx grid on. X label will be no, not this one, time, and y-axis is going to be noisy signal or received signal. So if we run it now, we'll have two pictures like so. And what we want to do now is to somehow to try to read this noisy signal. Now, the most primitive and simple receiver operates as a threshold comparison device. Yes, so basically you have to specify some certain threshold and say everything that is above it is 1, everything that is below it is 0. As simple as that. So it's written also in description here. That's how we are going to create our receiver. So if a signal level is more than 0.5, we consider it to be 1, otherwise it is 0. And we will use a very simple threshold device here. Like we don't really want to know average or whatsoever, or squares or energy. We just compare 1 point per point. Yes. Now, it's of course not how it exactly is done in the real life, but it still is very fast and pretty straightforward. And it works if the noise is not too strong. We'll try to increase the noise and see what happens to our receiver then, and there will be some problems. Yes, so task 4, receive the signal by comparing with threshold of 0.5. Now you may ask why 0.5, why not 0.3, not 0.4, and so on. That happens to be because our signal values are limited either to 0 or 1, and the middle point in between that is precisely 0.5. So if we were limited to 0 to 5, then that would be average point 2.5, yes? So in a sense, we can actually calculate this threshold even accurately in here. So let's do this, yes? Let's say that threshold is equal to, basically, we want to know the minimum value of our original signal S and maximum value, and their difference divided by 2. So that is going to be maximum S minus minimum S divided by 2, like so. And if we run it, you will see that threshold is indeed 0.5. That's how it came to be, yes? I want now to actually mark this threshold as a dotted line on top of here for later to easy compare. So I'm going to say, okay, to my previous plot here, hold on, make a new plot. Now I want to create a plot of line. As you know from the school, from mathematics, to construct a line, you only need 2 points, starting and ending points. You don't need everything that is in between. So our starting point is pretty simple and straightforward. It's 0. Our ending point is also simple. It's n. Yes? So we specify an array here from 0 to n, that is x-axis, and y-axis has this threshold at the starting point and threshold at the ending point. So that will construct a horizontal line. And all I need to do is to say that its color should be red and it should be dotted. And then I say hold off to, you know, mistakenly not to plot anything later again on top of that. So if I run it now, you will see this. Well, actually, it's difficult to see even on my screen, but it is consisting of dots. Well, let's use dashed one instead then, with two minuses, yes? Well, now it's more like so. So logic of our receiver is very simple. If we are above it, then that reads as 1. If we are below it, that reads as 0, which is actually what was indeed sent. Yes, that's actually true. So how are we supposed to achieve that? In Matlab, there are comparison functions like so. Yes, so for example, I can say 2 more than 4. And of course, it's not true. So Matlab is going to say 0 as a false. If I say differently, like so, it's going to say that it's true. And similarly, you can compare arrays. Yes, so let's say numbers from 1 to 10 are more than 5. So only starting with the 6, 7, 8, 9, and 10, that is true. For numbers 1, 2, 3, 4, 5, it's not true. Yes. So that is basically all that we need. Yes, as you can see, it says it's 0 if condition is not met, and it's 1 if condition is met. And what we want to do is to say that condition is compare our received signal, noisy one, with this red line, and then it should produce the answer. It's as simple as that. Yes, so compare received signal. So that is going to be, let's say, how did we call it here? SDT. So let's be consistent with the notations. Detected, yes, signal. That is SRX compared with threshold. Now, if it is more than threshold, it should read as 1. If it is less than threshold, it should read as 0. Now, I don't want to spam it, but I do want to see this as a new picture, preferably somehow together with this picture, but not on top of it. Yeah. So my option now is to use something called subplotting. Yes. There is a way to actually say I want to, instead of showing one picture in one window, I can show multiple figures, one beneath another, for example, in a column or in a row in one window. That is actually not so difficult to do. We need to go wherever we use the first one here after the figure. Yes, we don't want to change anything about this one. It should stay. But here, before running this, we should say that we want to have a subplot. Now, subplot is a matrix of plots. Yes, you specify dimensions, how many rows and how many columns. I want to have 2 rows, 1 column, and this particular plot, which I'm drawing right now, is the first one. So that will be rows, columns, number of plot notation. Yes. Accordingly, here now I can say subplot 2, 1, 2. That is going to be second plot. Now I don't need the semicolon. It doesn't do anything anyway. And say plot time as detected. Grid on, X label time, Y label detected data. Now if I run it, you can see that it actually produced this signal, although it's difficult to see here because of similar colors, so make it Let's make it red, maybe also even line with 2 to be really observable, or maybe green, not red, because red is something maybe not so good. Just to see it better. Okay, so now you can see that actually we have received the signal and cleaned it all the noise. Now this works smoothly because the noise is not too strong. However, in this practical exercise further, well, we are actually finished. Basically, yes, we will speak about NRZ next time, so we don't do it today. But if you are interested, it's not difficult to do. You just, change here and change the threshold. Well, I'll demonstrate that during the lecture, which we will have. But what we want to do now is to say in the task 4 or 6, repeat these steps for different SNR value of 10 decibel, of 0 maybe, yes? So all that you need to do now is to go at the beginning and say, now I want to have 10 decibel signal to noise ratio. Let's see how well it works then. Well, now you can see sometimes our 0, because of too strong noise, actually was able to go beyond our threshold. And because of that, our original data was not read properly. So what I want to do now is, on top of this green plot, let me also add one more plot that is our original data. So here I have to say hold on plot time as transmitted. Let's use some color, I don't know, magenta color, dashed line, hold off, so that we can actually see the original signal there as well, what it was supposed to be. Well, magenta is difficult to see here. Maybe red one will be better. No, it looks like I do need some line width. Okay, maybe not 2, but 1.5 to be better observable. So yes, now you can see that it actually should have been 1. Here it should be 0, all the way up to here, then 1, then 0, yes? But because of this constant random noise that sometimes occasionally passes through this threshold, our reading is not really consistent, yes? It's not like constant 0. Now we'll deal with that by actually averaging out this noise, yes? Because on average, you can see that this noise oscillates around some level. Now that will be our next first practical exercise, for which you will need to have report, but at this point you can simply play around by changing SNR and seeing for yourself that, let's say now I have minus 10 SNR. What that means is now our noise is 10 times stronger than a signal, meaning that, well, we have a very noisy signal received. Yes, as you can see, it's literally just noise and nothing else. Yes, we cannot read any data from that. Well, we'll see if this is as hopeless as it looks like. Well, actually, randomness here is a little bit funny. It's all zeros. Let me regenerate it. Yes, okay, so there is at least some 1 here. Yes, so in this particular case, of course, with our such primitive and very simple detector, it's not going to work just like that, yes? So this concludes our introduction to Matlab. I have recorded it, so we'll upload it as well, so you can check it, yes?